Thank you all for coming, everybody. We got a really exciting session this week. This week we're hearing from John McCann, a really interesting topic entitled What We See and What We Know, Partners in Human Vision. So I will just pass you over to the screen.
Well, good morning. My name is John McCann, and I'm here in Arlington, Massachusetts with my wife, Mary. And we are both graduates of Polaroid Research Labs, where we both spent 25 years, really enjoying life as research workers. Now, on this virtual tour, if you set sail from Bristol and sail due west but a little south, you'll come to Boston Harbor. And when you get to Boston Harbor, you are at the mouth of the Charles River, which runs through Boston on an east-west direction. And if you go up the Charles River, you'll pass MIT on the right. Behind MIT is the Polaroid corporate headquarters and research facility and engineering facility. And if you go a mile further west, you'd run into the Harvard campus. And if you go still 2 miles further west of that, you'll come to the Arlington, Cambridge, Mass boundary, and we're just over 1,000 yards over the boundary between Cambridge, and we live on a tiny little pond that you should be able to see on the screen briefly. So welcome to Spy Pond, and thank you for joining the talk. As I said, both Mary and I worked at Polaroid for 35 years, and I had the honor and privilege of working directly for Edwin Land, who was the founder and president, director of research of Polaroid. And so if you go to the slides now, Damien, please.
Sure, I'll just bring that up. Just take a second to catch up. There we go.
Go to the first slide. The Polaroid research environment was really special. It was a real lab. Whenever an experiment went wrong, that was not a source of shame or a problem. It was a great opportunity. Land had all these funny little sayings that he would say around the lab, like, science is the technique of keeping yourself from kidding yourself. Or every great invention is a sudden cessation of stupidity. And then he would necessarily quip that that's a necessary but not sufficient condition for a great invention. And he would say, always test the opposite of what you believe. And so at the Polaroid lab, nothing was more exciting than an experiment that went really bad. A well-planned experiment, A, to test hypothesis, B, for the expected right, C, when you got Q prime as the result, that was a moment for celebration. And I wanted to share with you one of those moments. And next slide, please. For those 35 years at Polaroid and since, I've been interested in human color vision and computational models of color vision. And so it's a mixture of art, science, and one of the other very influential members of the Polaroid research team was the annual visit by Ansel Adams, the great American photographer. And so much of the lab was involved in the kinds of things your lab's involved in, the interface of art and science. As a corporate member, one of my first challenges in 1970 was I had to go to the Polaroid Corporation's treasurer. And it was like going to the principal's office. I had to go to his office and I had to make a presentation to explain the purchase of that cost $16,000 for hand-wound computer core. Now, just think, that was 8K of hand-wound memory. Today, my laptop has 2 terabytes, and the cost per terabyte today is 1/10 of a penny cost per kilobyte is 1/10 of a penny. So my laptop has 1 billion times more memory than the Polaroid Research Lab in 1970. And the memory cost 1 part in 2 million. That's a cost benefit improvement in terms of cost per kilobyte of 10 to the 14th. So you can see the wonderful digital world that allows us to talk here this morning has changed the world just remarkably, both in price and convenience. And it has its bugs, but we'll get through them. Now, what I want to share with you is this interest in color vision and what you do to explain color vision. The problem goes back to Aristotle, and we'll talk about that more. So I'm walking down the street in Boston, and I see the shadow that's on this tree. And it's a perfectly beautiful day, and it's an ordinary tree, and there's a shadow on it. There we go. As I got closer to the tree, it started to bother me. Something didn't look right. Next slide, please. I looked around, and there was nothing shadowing the sun. There weren't any buildings or anything in that direction. It was a great big open space. Next slide. It was blue paint. Next slide. Someone had gone to the trouble of painting the bottom half of the tree branches blue. Next slide. There was no shadow cast on the tree. There's blue paint on the tree that made me see a shadow. Next slide. Well, what did I mean? I said I saw a shadow on the tree. I saw a part that was darker and bluer. Some people call that a sensation. I had a perception that part was in shadow, a cognition. I recognized that part was an absence of sunlight. I learned that paint was darker and bluer. I saw a shadow on the tree. Next slide. Why was the shadow still there after I knew it was blue paint? Now, what we're wondering about this morning is, what do all these words mean? Sensation, perception, recognition, knowing, conscious, unconscious, inference, bottom up, up down. These are all words we use every day to describe our vision. And our human vision is a central part of everything we do in almost every field of study and in technology. Vision is such an important part, but we don't really have a good enough vocabulary to describe what it is we are seeing. Next slide, please. Do we see so as to learn, so as to know, or do we know certain things by the way we are built that influences the light that's falling on the retina and going up the visual system to influence what we see? This is the nurture-nature argument that's been going on since Aristotle. When we learned that we've been fooled, should that knowledge have changed what it is we're seeing? I learned I was wrong, but that had no effect. And I found that very curious. Next slide, please. We changed our minds, but we don't change appearances. Next slide. This is true when we see a great trompe-l'oeil painting. The fresco of Loyola is, you can see all the way to the heavens, and it doesn't bother you that it's a barreled roof, and there's no increase in depth in the sky. Next slide. There's no dome in this barrel ceiling. Next slide. There's no depth in this painting. It's paint on wood. Next slide. We all know about the Mueller layer illusion. We all know that the middle line is the same length as the top and bottom line, but we don't see it that way. Next slide. Even when we try to convince ourselves that they're the same length by painting the lines red and by drawing lines to prove that they're the same actual length, we don't see it that way. Next slide. These two women, the young woman and the old woman, coexist. We look at this picture, and at times we see one, and at other times we see the other. Sometimes we think we can control it by where we look. Sometimes we can't control it at all. What we are seeing is this complex mixture of the light that's coming in and the neural processing that is analyzing it. Next slide. Again, in Aristotle, you see this discussion of what shadows are and what surfaces are. Here's just a simple photograph of an attic. The walls, there's a slant ceiling wall and two vertical walls. They all have different appearances. They all have different lightnesses, but they are identical surfaces. They have identical paint on the plaster. Next slide, please. If you try to sort this out, because in vision literature, there's a lot of discussion about whether, it came out of Herring's discussion of color constancy in the late 19th century. He was concerned that appearances of objects was constant despite changes in illumination. Helmholtz, the physicist, turned to psychology or neurophysiology and suggested that, oh, humans discount the illuminant. And so we don't see the illuminant. Well, we did the experiment of, does it matter whether the surface is light that's falling on the object, or is it the surface of the object that's important, or does vision just not care? And so the experiment consisted of having a cube and a scale of lightnesses on the left. On the right is another scale of lightnesses, like the Kodak grayscale. So it's just an example of that. But we took these gray patches and put them on a constant white surround. And we looked at the cube. And as you look at that cube, you can see that there are three different lightnesses. The bottom right looks like the light's coming from the right. The bottom left looks like a shadow, and the top looks like a different lightness gray. Now, in fact, it's more complicated than that, because we took the cube, painted it all white on all six sides, and then took three of the sides and painted them with different gray paints. So there are edges in reflectance due to the paints, different paints on different surfaces. And there are edges in illumination cast by shadows and just the change of orientation of the surface to the light source. So we went to the trouble of doing all this. Next slide, please. I try to change the slide here. This is what the observer looked at. The block was on a black background this is too much reflected light from a white table. And the observer chose the light number on the left that matched the appearance of the three faces of the cube on the right. Next slide. Now, this is the data for 2 observers, and the bottom line was that the observer didn't care whether it was surface or whether it was illumination. The edges controlled it, and it didn't matter how you made the edges. Next slide. Many years ago, I was at HP Labs, and Don Greenberg from Cornell was visiting at the same time. And Don had done a lot of the early work on PRDF, all this ray tracing that's so much a central element in computer graphics today, and all the movie effects and all the computational things we see that look completely natural today. Began with a lot of this ray tracing of illumination falling on different objects in complex scenes. And that was Don's specialty. I was describing to Don this funny cube with different painted surfaces on it. And I rotated the cube. We were outside at although it was January in Palo Alto, it was warm enough to be heavy. The cafeteria had a table outside, and sitting outside in the bright sunlight. And I was showing Don this cube with the painted edges. And when I rotated it in front of him, he jumped out of his chair, knocked his chair over on the ground, and shouted, "You've moved the sun." Now, of course, I hadn't moved the sun, but he pointed out that when you play around with edges like this and you move edges, it looks like you've changed the illumination, not like you've changed the edges. And the next movie, if it works, will be a demonstration of that. So here's a movie of a cube. As you see, it looks like there's a bright sun over on the left. But as I rotate the cube, now the sun is over on the right. Now, this is just the painted cube. We're outside. There's a singular sun. The sun didn't move, but this is what it looks like. When the edges can tell us what the illumination is, but the edges, the illumination is not discounted, it is not made to go away. It's a crucial part of our vision, but hopefully you'll see that the sun is coming from the left now, but if we rotate the cube, the sun will come from the right. Next slide, please. We know that we're moving the reflectances, but we see the illumination moving. Next slide. So let's return to the initial problem here of what do these words mean when we come into something like, I see a shadow. Next slide. Another favorite experiment was that on a summer vacation on a lake in New Hampshire, there was this raft out in the middle. It was early morning. The kids were still asleep. And I'd been spending some time talking with Alan Gilchrist about how do you do a psychophysical experiment measuring lightness. And my feeling was that you would ask the observer what he saw. And Alan's insistence was that you ask the observer what the object is. And so to make some sense out of this, I took this photograph because I thought it was a wonderful example of the questions you ask the observer about the surface of that raft. Next slide. If I didn't have a floating spectroradiometer, but my best guess was that the sunlight was about 4,000 degrees Kelvin, and it was about 10 times brighter than the shadow face. The shadow face had 20,000 degrees Kelvin roughly, and was 1/10 the brightness. So very different spectral radiances. Next slide. Now, the question that I talked about, my question versus Gilchrist's question, has a big effect on your answers. Next slide. I can remember while in college, I read in this a really exciting page-turning book called Optical Society of America's Science of Color, these definitions of sensation and perception. Sensation they defined, and this is the work of a committee that took 25 years to come up with this answer, a mode of mental functioning that directly associated with the stimulation of the organism. And perception was the mode of mental functioning that includes the combination of different sensations and the utilization of past experience in recognizing the objects and facts from which the present situation arises. I turned to my roommate and read them this passage and asked him, what do you think they were smoking? What are these guys talking about? But 20 years later, I found a place for it. In painting, if you go back to the Sung dynasty, these children were portrayed by their surfaces. There's very little shadows and variability of illumination. The idea of the artist was to paint the object. But if we go to the next slide and look at a Monet painting of his wife, we see that his rendition was the object plus the light. You can see that his wife is in shadow, and the colors and distribution and lightness scale are all used to render the appearance and not the surfaces. Next slide. And another great painter, Karina Perelman, did a remarkable experiment as a part of the 2007, I guess it was, CREATE program of Brisco, in which she painted the appearances of a high dynamic range scene and a low dynamic scene made out of the same surfaces. Next slide. We made two identical sets of painted blocks. All the paints were the same, all the shapes were the same, and we just had two duplicates. On the left, we had a low dynamic range image by illuminating it uniformly, and as best we could by using an illumination box. On the other scene, the high dynamic range scene, we used a spotlight and some floodlights that were made of slightly different illuminations. So we had an easy scene to reproduce and a difficult scene to reproduce when it comes to photography. But what we cared about is what it looked like. Next slide, please. And so the paintings on the bottom are these fabulous images that Karina painted that are what she saw when she looked at the scenes that made the photographs in the top part of the scene. Next slide. If you look at the white block, the low dynamic range white block painting on the right side of this slide, that's the 30, 20, 33, 9, and 18, and you measure the spectral reflectance of those paints that Karina used to reproduce that scene, you can see color constancy. You can see that the paints that were chosen are pretty much the same. Slightly different, slightly darker as the objects were in shadows. When we look at the high dynamic range scene in the next slide, in the bottom right, you can see that that same square had a lot more going on. You can't see it terribly well, but that's in the center picture, the right-hand side, that's the high dynamic range. You can see that Karina selected a variety of different color paints to match the different appearances of that singular white paint surface in the scene. And so this is a very interesting example of using Karina's painting skill to quantify the sensations that the observer sees in these real-life high dynamic range scenes. This is, you can't see it at the bottom, but this is a paper with Karina and Ellie Rizzi and myself. It's published in Frontiers. Next slide. So to come back to the raft, if you ask the fine art painter question, the Monet Paraman question, what does it look like? You would use white paint with a little bit of yellow on the right surface of the raft, and you would use a little bit of gray and a little bit of blue for the left surface of the raft. And so this is the fine arts painter question. Next slide. You can see if that's a photograph of the scene, that's what you would do. You would not use the same paint to reproduce the appearance of the raft. Next slide, please. Perception, or the Gilchrist approach, is what you do is you ask the observer what paint is on the raft. That's the house painter's question. Next slide, please. If the painter came by and you said, please go out and paint that raft, just make it the same as it is, the painter would not swim out with his swatch book to match the surfaces of the two faces. He would take a look at it, go directly to the hardware, buy a can of white paint, and put white paint on both things. So the house painter answer is, next slide, that in a world of reflectances and illuminations in the right column, those are identical things. We can recognize that the surfaces are painted with the same paint, but at the same time, if we want to measure the color differences, the appearance, and we want to look at the world through the filter of edges and gradients, we would say they're slightly different. If we want to look at it with pure physics, we would say they're entirely different. They're very different. And so there are many answers about the same objects we look at. And some people would call the physics solution is the exact copy. The sensation, the edges and gradients, people talk about it as a bottom-up model. And the reflectances and illumination, the perceptual people talk about it as a top-down model. We have to fit the world into our recognition of objects. Next slide. So in 1967 landed the black and white Mondrian experiment. And here we have a gradient of illumination falling on this black and white collection of papers. There's a light paper at the top and a dark paper at the bottom at the tips of the two arrows. Land would give the talk, and my job was to crawl around the floor and move the light, so the meter said that the same amount of light came at the tip of the arrows. The two tips were identical. Next slide, please. 20 years later, Ted Adelson came along and essentially did the same experiment, but proposed that the top-down version of the same experiment. A and B in the right-hand slide are the same digital value in this digital simulation. So the bottom-up, the Land and McCann bottom-up, used this experiment, the black and white Mondrian, as the poster child for bottom-up processing. And Adelson and colleagues used the same experiment as the poster child for top-down perceptual processing. Next slide. The top part of this slide shows the, it describes it as the top-down model. However, if you use negative light, it still works. And as you can see in the edges and illumination argument said, well, the tower isn't necessary. And in fact, most of the scene isn't necessary. It's all really just about the edges and gradients to create the appearances we see there. Next slide. So there are two major frameworks in thinking about color and appearance. One is the physics-based, and anything that has CIE in it is based upon color matching. These are experiments of different wavelengths in a black room and a black surround. The only thing in the field of view is a single spot of light at the end of the experiment. And you look at the arrow there, you look at the circle around the rods and cones at the top of the picture. And so a very small region of the light falling on the retina is the only thing that's allowed in any CIE computation. So everything in CIE space is the result of molecular reactions that happen at a scale of angstroms. Visual appearance is different. Visual appearance, the blue part in the bottom, uses all of the visual pathway and uses a field of view of something approximating 180 degrees visual angle. So these are two very different ways of looking at the world. But now, how do we make a framework? And let's have some fun here thinking about the top-down, bottom-up framework of vision. Next slide, please. So we have the world, and light comes and falls on the retina. What happens in a tiny patch of the retina is the basis of all CIE colorimetry. But the story doesn't stop there. We have all the rest of the visual processing that creates vision at the other end. Now, sensibly, the psychologist might want to use the left to right analogy or the front to back analogy, but that it's a little more complicated than that. They use the bottom up, top down analogy. Next slide, please. So we're going to move the observer to fit the language. And we know certain amounts about the neurophysiology of the light coming from the world and going into the cortex and how it travels around the cortex. Next slide. The perceptual people like to think about the signal coming in being processed and having a feedback loop so that the appearance is modified by the cognition at a higher level. And if you want to have what you know influence what you see, you have to have some type of framework like this. Now, the actual physiology is very complicated, and there's no time to do that. So let's do some very crude representations of the kinds of approaches you could use. Next slide, please. So what we want to talk about is what's our favorite way of thinking about how vision at the top gets there from the world's light at the bottom. Next slide, please. Here's the model built upon interconnections. You can see that from a large part of the truck below, there are many connections. This uses Poisson random connections to get from the bottom to the top. Next slide, please. This is the homunculus view, that there's a single path from the bottom, from the truck that goes to the cage, it goes to the bucket, which goes to the ladder to get to the cortex. Next slide, please. This is the strictly local environment, no sense going looking around distant ladders when you have 15 gallons of paint to just put it to better use. Next slide, please. This is the natural model. And next slide. This is, I have no idea what these guys are doing. Next slide, please. This is the dustbin model. Next slide. And this wins the engineering award. The thought that went into this is much better than the other examples. You can see it's the principal elements are a table and a picnic bench and two picnic benches and a table. The benches are arranged perpendicular to the house. The table is arranged parallel to the house. Two supersized cinder blocks are placed on top of the table, and the unfolded folding ladder is used to get to the top. Next slide, please. My favorite view is it all happens simultaneously, just like the picture of the old woman and the young woman. These things all go on at the same time in different parts of our analysis. So what we need to do to get a better grasp on how we see is to work on our language. What do these words mean? And more important, when you explain these words to somebody, you've got to be very careful to explain your definition, because when I try to do that with people, I usually find their definition is different from my definition. And so these words turn out to be terribly important about what we think's going on, because, as I say, this problem has started back with Aristotle, and this is the part of vision that requires more work, because the technology has come so far and the color rendition has come on so far, but we really need to think a lot about what we mean when we talk about all this. Next slide, please. We sense, we perceive, we recognize, we know, all of these things coexist. We just need to remember to take care about the words we use and the assumptions we make. Next slide, please. Remember, language helps us collaborate, and collaboration is important. Thank you very much.
Thank you so much, John. I always say it's a little bit strange not to be able to clap these things, but we've started using a few clapping pictures in the chat, so that'd be great. But thank you, that was absolutely fantastic. Would you be happy to stick around and field a couple of questions?
Absolutely.
Yeah, sure. So if you do have a question in the chat, just raise your hand. I'll get things started. Yeah, you talked a lot about perception and that link between the eye and the brain. Obviously, there's a lot of things that can vary from person to person in that. I was just wondering if you thought, we have hope of incorporating all those differences in perception into these kind of models.
That's a problem that's bothered me since 1960. I don't think there is a solution to the philosophical question, is my green the same as your green? And so I set that aside 60 years ago and went on to the question is, does Mary select the same chip in the Munsell book as I do when we're looking at the same object in the same illumination in the same ground? Now, most of the time, it does. And so, with minor differences, if you go to the trouble of making a match of any scene to a particular color atlas, like the Munsell book in fixed illumination, you have a measure of its appearance. You can make a computer model to calculate the appearance match the observer made. And that allows you to understand the hardware that's helping us see what we see. But we can't, you can learn some interesting things. We have both just gone through bilateral cataract surgery. So we spent, when we had one eye with the old cataract and one eye with the new plastic lens, we did a lot of observing of the filter that would make the two eyes match. And an interesting result from that was we did this experiment for 100 days between the two operations, between the removing the first cataract and removing both cataracts. we found there was no color adaptation in that period. So there are loads of things you can do to model vision and understand the process without ever having to address the philosophical question, do I see what you see? Because, and in a sense, that's what we do when we use a meter stick to measure the length of something. We have a standard, and we want to measure the length of the pin. We put the standard next to the pin, and we see how long it is. Well, we can measure color sensations and model that with a computer imaging by using that standard.
Oh, fantastic, fascinating. Steve, you want to go ahead and I'm pretty sure you can unmute yourself.
Yeah, I can. Hi, John.
How are you? Great to hear from you.
If I look across a field at a hedge, it appears in the distance as black or very dark. If I walk across the field up to the hedge, then it's obviously going to be a whole mass of greens and other colours. Now, I'm still always struggling as to whether that's colour appearance or whether that's, well, I don't know. Do you know what I mean? How would you describe that?
Well, it probably is a whole bunch of different things. If it's really far away, you have to worry about atmospheric haze. Recently, we've become very interested in scattered light. And so I've always been very careful to model everything I did by making precise measurements of light coming from the object to my eye. And in recent years, done a lot of work that showed that what's in the image causes different scatter, and scatter is much larger because our visual system is good at discounting the scatter. It doesn't discount the illumination, but it does discount the scatter. So I would think it's got to be part physics, part optics, part size of the image. Blue things are particularly bad at changing they get very black if they get small. And so it's simply because we don't have any blue receptors in the retina. So it's hard to chase. There's probably a dozen different things that are a part of that story.
That's right.
Karina, go ahead.
Hi, John. Mine kind of follows on from Steve's as well, but looking more about, and also in relation to scatter, in relation to kind of texture, and so the difference between kind of color as a flat surface, as in a paint chart, compared to something where we're photographing lots of kind of images which have lots of different textures, micro surface appearance. So how does that then relate to the appearance of color as something which is a flat color as opposed to something which is much more complex that you would see in a photograph?
Well, Mary's expertise, as you know, is in microscopy of films and photographic films, and the surface structure plays an enormous role in the light surface interactions. If you take a pigment and put it in a material and it's perfectly flat, the light that's coming from that is going to be very different than if you make a three-dimensional surface, and the bigger the surface structure, the more the light coming back to your eye or to the camera is going to be very different. So there's the pigment part, there's the physics of light interacting with the structure of the pigment, and then you get to the eye, which has very different spatial frequency responses depending upon the size and the position on the retina. So I doubt there's one simple answer to that story, but you have to chase it all the way through all the physical and the physiological things. Would you agree with that, Mary?
Yes.
She nods her head.
Fantastic. Okie dokie. We should probably wrap up there. So just a couple of thank yous. Thank you, Angie, for helping out and making sure this all ran smoothly. Thank you, Karina, for setting this up in the first place. Thank you to everyone that turned up. It's been a really good response. But most of all, thank you very much, John. That was absolutely fascinating.
Well, thank you all. It's been a great pleasure to be virtually with you.
Thanks, everybody. Cheers.